Hi friends, welcome to the next session of the subject Engineering Mathematics. Now in this session, we discuss the concept of eigenvalues and eigenvectors. In the last session, we have discussed 70% of eigenvalues concept. We continue eigenvalues concept followed by eigenvectors concept. Now let us see what should be the eigenvalues of a real symmetric matrix. Eigenvalues of a real symmetric matrix. Suppose I have a matrix A, square matrix. This is a real symmetric matrix. Real symmetric. What do you mean by real matrix? All elements inside this matrix are real numbers. Generally, we have real numbers and complex numbers. But inside this matrix A, all entries are real numbers. And symmetric. Symmetric matrix means A equal to A transpose. So when something is a real symmetric matrix, all eigenvalues of A are real only. All eigenvalues of A are real. This is very important point. It has been asked in the examination more times. Even 25 times it was asked in GATE directly or indirectly. Sometimes mostly in 90% cases it was asked very direct statement. So what is my conclusion? All eigenvalues of a real symmetric matrix are real only. Note down this point. All eigenvalues of a real symmetric matrix. All eigenvalues of a real symmetric matrix are real. All eigenvalues of a real symmetric matrix are real. Now in the same way, let us see what will be the structure of eigenvalues of a real skew symmetric matrix. Real skew symmetric. So here I am going to add one more term. This is real skew symmetric. So that means A is equal to minus A transpose. So therefore I am working with real skew symmetric matrix. Real skew symmetric matrix. In that case, what will be the structure of eigenvalues of A? Let us start with simple example. Suppose I have A equal to 0, 2, minus 2, 0. Now inside this matrix, I elements are 0, minus 2, 2. So all this is a real number, this is real number, and this is real number. So this is a real matrix. And of course, in this case, when you verify its transpose, it satisfies the condition A equal to minus A transpose. Therefore, this is a skew symmetric matrix. This is a skew symmetric matrix. Therefore, this is a real skew symmetric matrix. Now, let us try to find its eigenvalues. So, apply the definition, characteristic equation, det of A minus lambda I equal to 0. So, subtract lambda from diagonal elements. Here, my diagonal elements are zeros. So, this is a determinant of minus lambda 2, minus lambda equal to 0. And this implies lambda square plus 4 equal to 0. Now, this is a second degree equation. When we solve this equation, we get two roots. And one root is 2i. I call it as lambda 1. Second root, I call it as lambda 2. This is minus 2i. Now, they are complex numbers. Even this is also a complex number. Now, moreover, these are complex numbers and they are purely imaginary complex numbers. Purely imaginary complex numbers. See, when you have a complex number, it has a structure like this. Complex number structure will be like this. Alpha plus I beta. This is complex number. In this case, alpha is called real part. And this beta is called imaginary part. This is called imaginary part. So therefore, this is nothing but a general structure of complex number. Here I is some number, for example, whose square is minus 1. This is very clear to all of you. So if real part is 0 and imaginary part is non-zero, such numbers are called purely imaginary complex numbers. Alpha is real part, beta is imaginary part. If alpha is 0 and beta is non-zero, then this is called a purely imaginary complex number. When you observe this one, there is no real part. There is no real part. So this is, they are the complex, the eigenvalues are purely imaginary complex numbers, right? Suppose when I take this example, A equal to null matrix 0, 0, 0. This I can treat it as symmetric matrix, but I am expecting skew symmetric matrix. So even this is a skew symmetric matrix also. Elements are 0. So it is a real skew symmetric matrix. Real skew symmetric matrix. Now when you find its eigenvalues, my eigenvalues are 0. Now this is a real skew symmetric matrix, eigenvalues are 0. This is a real skew symmetric matrix, so my eigenvalues are purely imaginary complex numbers. When you look at 3 by 3 skew symmetric matrix, when you look at 3 by 3 skew symmetric matrix, I am increasing the size of a matrix. So at first my focus is find what will be the structure of eigenvalues of a real skew symmetric matrix. Very, very important area. Eigenvalues of real skew symmetric matrix. Real means all elements inside the matrix are real. Skew symmetric means A equal to minus A transpose. So when I start with this example, 0 to minus to 0, my values are in the form 2i minus 2i, purely imaginary complex numbers. When I take that example, A equal to 0, 0, 0, now my eigenvalues are 0. That means the eigenvalues of a real skew symmetric matrix are either 0 or purely imaginary. This is the most important point. What is that point? The eigenvalues of a real skew symmetric matrix are either 0 or purely imaginary. Now you can ask me one question. If I take a 3 by 3 real skew symmetric matrix, as I mentioned earlier in the last session, while during classroom workbook questions, we had gone through one question, the determinant of a skew symmetric matrix of size 5 cross 5, its value is 0. And in this session, today I mentioned that the determinant of a skew symmetric matrix of odd size is 0. And today one point is, if A is a singular matrix, its det is 0. So when you combine these 2 points, let me tell you 2 more points. One point is the determinant of a skew symmetric matrix of odd size is 0. Second point is, if something is a singular matrix, one of its eigenvalue is 0. When I combine these 2 points, what I get is, if something is a real skew symmetric matrix of odd size, implies at least one of its eigenvalues is 0. Got it? Very, very important point. I will tell you once again. 2 points, let me tell you once again. First point is, the determinant of a skew symmetric matrix of odd dimension is 0. And in this session, we have mentioned, in the last session, we have mentioned, if something is a singular matrix, then its det value is 0. That means when you combine these 2 points, the conclusion we get is, if A is a real skew symmetric matrix of odd size, implies at least one of its eigenvalue is 0. That is one conclusion. And in this case, all eigenvalues of a real skew symmetric matrix are either 0 or purely imaginary. Note this point. Note 1. All eigenvalues of a real skew symmetric matrix. All eigenvalues of a real skew symmetric matrix are either 0 or purely imaginary. All eigenvalues of a real skew symmetric matrix are either 0 or purely imaginary. Purely imaginary. Second note. If A is a real skew symmetric matrix, if A is a real skew symmetric matrix of odd size, if A is a real skew symmetric matrix of odd size, then 0 is one of the eigenvalue of A. Then 0 is one of the eigenvalue of A. then 0 is one of the eigenvalue of A. Now you note down example 1, example 2. This is example 1 and this is example 2. Now suppose if I take a 3 by 3 real skew symmetric matrix with rank 2, then two eigenvalues are non-zero. Of course, they must be purely imaginary. One is alpha I, second is minus alpha I, and third eigenvalue is 0. Suppose if I take this one, A equal to 0, 2, minus 3, minus 2, 3, 0, 0. For example, now suppose if it is 8, then this is minus 8. Now when you look at this, this is A equal to minus A transpose. All elements inside the matrix are real numbers. 0 is a real number, 2 real number, minus 2 real number, 8 real number, minus 3 real number, minus 8 real number. So it is a real skew symmetric matrix. Real skew symmetric matrix. Of course, that will be 0 definitely because size is odd 3. This is odd size. Therefore, its det is 0. One of its eigenvalue is 0. And since its det is 0, rank should not be 3. But this is a 2 by 2 submatrix whose det is not equal to 0. This is det of 0, 2, minus 2, 0. So this is nothing but 4. This is not equal to 0. Now therefore, in this case, its det is non-zero. Therefore, there is a 2 by 2 submatrix whose det is not equal to 0. Therefore, the rank of this matrix A is 2. Since its rank is 2, it has two non-zero eigenvalues. Therefore, if you want eigenvalues of this matrix structure, one eigenvalue is 0, second remaining two eigenvalues will be in the form alpha I minus alpha I. 0 alpha I minus alpha I. So therefore, you take any skew symmetric matrix of odd size, eigenvalues will be either 0 or purely imaginary. In the last two examples, for the first example, both the eigenvalues are purely imaginary. In the second example, both the eigenvalues are 0. But whereas in this case, few eigenvalues are 0, few eigenvalues are purely imaginary. Note this example. If you want the value of alpha, you calculate by using characteristic equation. But of course, that is not our situation. Just you get the structure of eigenvalues. One is 0, another is alpha I, second is minus alpha I. Definitely alpha is not equal to 0. So these are purely imaginary. I hope this example is very clear to all of you, right? So in the examination, if they ask you the eigenvalues of this matrix, assume that options were given. Then if it is a real skew symmetric matrix, then apply this property. Then you can easily eliminate options. You can get the answer very easily. You need not go for characteristic equation, right? Suppose if unfortunately all options are satisfying trace property and all options are satisfying det property, very rare occasion. In that case only we need to go for characteristic equation. In 90% cases it is not required to go by characteristic equation, right? So try to understand all properties. Whenever all properties are very clear, when you are writing examination, try to implement all these points. So revise as many times all these points. So formulas are very important and tricks are very important. You don't blindly follow characteristic equation. Characteristic equation is very useful if all these points are not applicable in your examination. So at the end, give the last priority to get the eigenvalues by discussing characteristic equation. In 99% cases, characteristic equation is not an issue. It is not required basically, right? That is definition. Now, based on these points, I can discuss one more point. The point is this. Suppose if alpha plus I beta is an eigenvalue of a real matrix A. Real matrix. I don't know whether it is symmetric or skew symmetric. General matrix, but elements inside the matrix are real. So if A is a real matrix whose eigenvalue is alpha plus I beta, then for this matrix another eigenvalue is alpha minus I beta. Basically this is nothing but a complex conjugate of alpha plus I beta. So replace I by minus I. This is imaginary number. When you replace I by minus I will get another number that is called complex conjugate of this. Because the complex roots will come as pairs. So if something, because this is a root of characteristic equation. Basically what is an eigenvalue? Eigenvalue is nothing but root of a characteristic equation. So when a complex number is an eigenvalue, then its conjugate becomes an eigenvalue of same matrix. But here the important point is it must be a real matrix. If it is a complex matrix, this point is not applicable. Let me give one example. Suppose if I take the matrix A equal to I 0 0 to I. Now this is a complex matrix. Of course this is a diagonal matrix, upper triangular and lower triangular. Upper triangular and lower triangular matrix. Either in this case or in this case my eigenvalues are diagonal elements. So here lambda 1 equal to I, lambda 2 equal to 2I. So according to this property, suppose if I miss this word real, then according to this property, if I is an eigenvalue, then minus I is an eigenvalue. If 2A is an eigenvalue, then minus 2I becomes an eigenvalue of same matrix. In that context, this 2 by 2 matrix will be having 1 plus 1 plus 1 plus 1, totally 4 eigenvalues. So which contradicts the original statement. So when something is a 2 by 2 matrix, it will be having exactly 2 eigenvalues. But whereas in this case, we are getting 4 eigenvalues. Why this property is violating in this case? Because this is a complex matrix. That is, some elements inside the matrix are complex entries. Therefore, this rule is valid only for real matrices. If A is a real matrix with a alpha plus I beta as one of its eigenvalue, then its a conjugate also an eigenvalue of same matrix. Right? Note this point. If alpha plus I beta is an eigenvalue of a matrix A, if alpha plus I beta is an eigenvalue of real matrix A, if alpha plus I beta is an eigenvalue of a real matrix A, then alpha minus I beta is also an eigenvalue of A. Then alpha minus I beta is also an eigenvalue of A. Now based on this point, we will make one more comment. So the number of complex eigenvalues of a real matrix is always even. If I have 2 plus I as an eigenvalue, then 2 minus I becomes an eigenvalue. If I have I an eigenvalue, then minus I becomes an eigenvalue. Of course, real matrix. Therefore, the number of complex eigenvalues of a real matrix is always even. Note this point. The number of complex eigenvalues of a real matrix is always even. The number of complex eigenvalues of a real matrix is always even. Now I discuss one more point. I have a 3 by 3 real matrix. 3 by 3 real matrix. So in the worst case, at most it will be having two complex eigenvalues. So rest of the eigenvalue will be real number. If I have 5 by 5 real matrix, 5 by 5 real matrix, see the dimension what I am discussing. I started with the 3 by 3. Next I am increasing the size to 5. So if I start with 3 by 3 real matrix, at the most it will be having two complex eigenvalues. That means the rest of the eigenvalue must be real number. If I go for 5 by 5 real matrix, at most it will be having four complex eigenvalues. So at most, maximum. So rest will be real eigenvalue. If I take 7 by 7 real matrix, at most it will be having six complex eigenvalues and the rest will be real number. So the conclusion from all these examples is, if A is a real matrix with a size odd, then real number at least it has at least one real eigenvalue. Let me repeat this. If A is a real matrix with odd dimension, then A has at least one real eigenvalue. Note this point. If A is a real matrix with odd dimension, if A is a real matrix with odd dimension, if A is a real matrix with odd dimension, then A has at least one real eigenvalue. Then A has at least one real eigenvalue. Then A has at least one real eigenvalue. Now let us discuss eigenvalues of some specific matrices. Suppose I have a matrix A equal to 2, 3, 4, 1. Suppose I have a matrix like this. Now when you look at this matrix, add all elements in column 1. This is column 1, C1, and this is column 2, C2. So here sum of column 1 equal to 2 plus 3, 5. Sum of column 2 equal to 4 plus 1, 5. Therefore, sum of C1 is 5, sum of C2 is 5. 5 is common. Therefore, 5 is one of its eigenvalue. If I take second example, suppose A equal to 2, 1, 9. Suppose 6, 6, 0. This is 2, or for example minus 2. This is 10. For example 10 plus minus 2, 8. This is 4. Now let us see in this case. This is R1, row 1. This is R2. And this is R3. So in this case, sum of R1, add every element in row 1. 2 plus 1 plus 9. This is 12. Sum of R2, 6 plus 6 plus 0. This is 12. Sum of R3. So 10 plus 4, 14 minus 2. This is 12. Now when you observe this matrix, the sum is common for all rows. This is 12, this is 12, and this is 12. Therefore, 12 is one of its eigenvalue. Therefore, the conclusion from this or this C, in this case it is 5. In that case it is 12. Without discussing its characteristic equation, without discussing its trace properties, without discussing its dead properties, I can easily say 12 is one of its eigenvalue and 5 is one of its eigenvalue. Therefore, this need not be positive value. You can have minus 2, minus 2, 1 by 6, 1 by 6. But sum must be common for all rows or sum must be common for all columns. Either for rows or for columns. In that case, that constant becomes one of its eigenvalues. Right? This is so powerful shortcut. Very, very, very important shortcut. In fact, it is valid for any n cross n real matrix. See, whenever we discuss matrix, by default it is a real matrix. Don't worry about complex entries. Whenever we discuss matrix, by default it is a real matrix. Even if we specify or if we do not specify, if something is a matrix, by default it is real. Wherever it is required, definitely we specify that, right? Now let us generalize this point. Suppose A is a n cross n matrix such that sum of C1 equal to sum of C2 equal to and so on, sum of Cn equal to k, or sum of R1 equal to sum of R2 equal to and so on, sum of Rn equal to some constant k, then this constant k is one of the eigenvalue of this matrix A. Note this point. Note, if A is a n cross n real matrix, if A is a n cross n real matrix such that sum of C1 equal to sum of C2 equal to and so on equal to sum of Cn, sum of C1 equal to sum of C2 equal to and so on equal to sum of Cn equal to k, or sum of R1 equal to sum of R2 equal to and so on equal to sum of Rn equal to k for some constant k, then k is one of the eigenvalues of A, then k is one of the eigenvalue of A. So to illustrate this point, note down example 1 and example 2. I will give more clarification how we are getting this uniform sum as one of its eigenvalue once I discuss eigenvector concept, right? We will discuss eigenvector concept within short span of time. Now, let us try to establish a relation between eigenvalues of A and A transpose. Eigenvalues of A and its transpose. See, as we know, trace of A equal to trace of A transpose. Det A equal to det of A transpose. I would like to establish a relation between eigenvalues of A and its transpose. So A is a square matrix. Definitely A transpose will be square matrix. So in that case, I can discuss directly eigenvalues of A and its transpose. So trace of A equal to trace of A transpose. This is very clear. Trace of A equal to trace of A transpose. Point number 1. Point number 2, det of A equal to det of A transpose. So based on these 2 points, we can say that eigenvalues of A are same as eigenvalues of A transpose. Note this point. Eigenvalues of A are same as eigenvalues of A transpose. Eigenvalues of A are same as eigenvalues of A transpose. Next we discuss eigenvector. Suppose A is a n cross n matrix. Since it is a n cross n matrix, it has n eigenvalues. Assume that they are lambda 1, lambda 2 and so on lambda n. Assume that lambda is one of its eigenvalues. So this lambda can be either lambda 1 or lambda 2 or lambda 3, or this can be lambda n also. So we have a n cross n matrix having n eigenvalues, lambda 1, lambda 2 and so on lambda n. Assume that lambda is one of these eigenvalues. Now my task is to establish a relation which connects a matrix A, we call it as original matrix, and eigenvalue lambda and eigenvector x. So I must establish a relation between original matrix A, eigenvalue lambda, and some matrix. In our context we call it as eigenvector, right? Let us see what will be the structure of eigenvector. Suppose if X is a non-zero matrix, X is a non-zero matrix of size n cross n, n cross n, because original matrix size is n cross n. Suppose if X is a non-zero matrix, zero matrix means all elements inside this are zero. Non-zero matrix means at least one element is not equal to zero. Zero matrix means all elements are zeros. Non-zero matrix means at least one element is not equal to zero. So therefore, if there is at least if there is a non-zero matrix X of size n cross n such that A into X equal to lambda into X, then this X is called eigenvector of this matrix with respect to this eigenvalue. Now let us see, this is one matrix, this is one matrix. Let us see logically whether it is true or not. What is the size of A? N cross n. What is size of X? N cross 1. Here dot is there. When you multiply these two, this will be eliminated, n cross 1. So this LHS is a matrix of size n cross 1. Now lambda is an eigenvalue. That means it is some constant. X is a matrix. So when you multiply a matrix with its constant, size will not affect. So but therefore this is also a matrix of size n cross 1. LHS matrix size is n cross 1. RHS matrix size is n cross 1. So part of the definition is very clear. Therefore whenever A dot X equal to lambda dot X, where X is a non-zero matrix, this is important, where X is a non-zero matrix of size n cross n such that A into X equal to lambda into X, then this X is called eigenvector of A with respect to an eigenvalue lambda. Because when you change eigenvalues, matrix is fixed, that is A. But when you change frequently eigenvalues, X values will be changed. So therefore, whenever I want to say this is an eigenvector, I must specify very clearly this is an eigenvector with respect to which eigenvalue. I must mention very clearly, right? Therefore, in this context, this X is called an eigenvector of A with respect to an eigenvalue lambda. X is called an eigenvector of capital A with respect to an eigenvalue lambda. So basically, what is an eigenvector? It is also a matrix, but size is n cross 1 and it is a non-zero matrix. That means if I deal with 2 by 2 matrix eigenvectors, the size must be 2 by 1. If I deal with eigenvectors of 3 by 3, it must be size 3 by 1. Of course, at least one element is not equal to 0. Therefore, whenever this happens, I say that X is an eigenvector of this matrix A with respect to an eigenvalue lambda. Is this clear? Right. Note this definition. Eigenvector. Let A be any n cross n matrix. Let A be any n cross n matrix and lambda be one of its eigenvalues. And lambda be one of its eigenvalues. Let A be any n cross n matrix and lambda be one of its eigenvalues. First of, if there exists a non-zero matrix X, if there exists a non-zero matrix X of size n cross 1, such that A into X equal to lambda into X, A into X equal to lambda into X, then X is called an eigenvector of capital A, then X is called an eigenvector of capital A with respect to lambda, then X is called an eigenvector of capital A with respect to an eigenvalue lambda. Now let us discuss one simple 2 by 2 matrix example. Suppose I have a matrix A equal to 8 1 1 8, 8 1 1 8. Now you can see 8 plus 1 is 9, 1 plus 8 is 9. So one of its eigenvalue is 9. 8 plus 1 9, 1 plus 8 9. Sum of C1, sum of C2 equal to 9. What is the trace of this matrix? 16. As we mentioned earlier, sum of eigenvalues equal to trace. So what is the trace of this matrix? 8 plus 8, 16. So lambda 1 is already 9. So lambda 2 must be 7. Therefore, these two are eigenvalues of this matrix. Now, let us try to find eigenvectors of this matrix with respect to this by using definition. My task is at first finding eigenvectors of this matrix with respect to this eigenvalue. So with respect to lambda 1, I will try to find. So my definition is A into X equal to lambda 1 into X. Of course, I will assume that the eigenvector with respect to lambda 1 is X1. So what is my matrix A? The matrix A is 8 1 1 8. Now this is a 2 by 1 matrix. So because we are dealing with the 2 by 2 matrix, eigenvector size will be 2 by 1. Assume that this is AB. What is lambda 1? This is 9. So 9 into AB. This implies this is 8A plus B and this is A plus 8B equal to this is 9A and this is 9B. Therefore, two matrices are equal implies corresponding entries are equal. This implies 8A plus B equal to 9A. This implies B equal to A. Even when you look at second equation also, A plus 8B equal to 9B, you will get the same equation. Therefore, at this moment, we got B equal to A. So that means you can assign random values. So therefore, in this case, if I assign A value 1, randomly B will be 1. If it is 2, this is 2. If it is 1 by 7, this is 1 by 7. If it is minus 6, this is minus 6. That means A comma B can be any real numbers. Can be any real numbers except 0. Except 0. Suppose if I assign one variable either A or B to 0, if I am not getting another variable 0, then I can assign. But unfortunately, when you assign A value 0, B will be 0. That means in the eigenvector, all elements should not be 0 at a time. Therefore, in this case, A comma B can be any real numbers except 0. Try to understand this point. So here B equal to A. I can write 0 equal to 0. Logically, this is true. 1 by 2 equal to 1 by 2. 7 equal to 7 like this. So I don't have any restriction on the values of A and B except at 0 moment. What happens if I assign 0 for A? If I assign 0 for A, then B will be 0. If I assign 0 for B, A will be 0. Therefore, A and B can be any real numbers except 0. If I assign one variable to 0, I am getting remaining value also 0. That should not be happened in case of eigenvector. As we mentioned in the definition, eigenvector is a non-zero matrix. That means at least one entry inside the vector matrix should not be 0. But in this case, when you assign one value to 0, rest of the values are becoming 0. That's why I am putting restriction on the values of A and B. So A comma B can be any real numbers except 0. Therefore, let me list out some eigenvectors. Few eigenvectors are like this. 1 1 is an eigenvector. A value 1, B value 1. Another eigenvector is this minus 2 2. Or I can do like this root 3 root 3. This is one eigenvector. Or for example 1 by 9 1 by 9. So all these are nothing but eigenvectors of this matrix with respect to this eigenvalue. Now interestingly, when you look at this with respect to same eigenvalue 9, the same matrix is having infinitely many eigenvectors. Now this is an eigenvector of same matrix with respect to 9. This is an eigenvector of same matrix with respect to 9. Eigenvector with respect to 9. Eigenvector with respect to 9. Basically all these are multiples. You can see this is minus 2. Now you can see this is minus 2 times of this. This is root 3 times of this. This is 1 by 9 times of this. Therefore, the conclusion from this example is, if x is an eigenvector of a matrix A with respect to an eigenvalue lambda, then k into x is also an eigenvector of same matrix A with respect to same eigenvalue lambda, where k is any non-zero constant. Therefore, with respect to one particular eigenvalue, a particular matrix will have infinitely many eigenvectors just by taking non-zero multiples. Got it? So this is minus 2 times of this, and this is root 3 times of this. This is 1 by 9 times of this. Therefore, like this you can produce infinitely many eigenvectors. So it is valid for any n cross n matrix. See, you give me any 3 by 3 matrix. You give me one eigenvalue and one eigenvector. Based on that, I can produce infinitely many eigenvectors. So this is valid for any 2 by 2 matrix, any 3 by 3, any n cross n real matrices. So therefore, with respect to one particular eigenvalue, a real matrix will produce infinitely many eigenvectors. So in the examination, either GATE or Transcore, IES or whatever it is, if they ask you to find one of the eigenvector of original matrix, just you find the eigenvector either by shortcut or by definition. I discussed shortcuts within short span of time. Suppose if you get eigenvector as 1, 4. Unfortunately, if it is not there in options, don't think that the procedure is wrong. Look at the multiples of 1, 4. If any multiple of 1, 4 is there in options, you can opt it. That could be a right answer. Just by this. Okay? Work out this. Note, if A is a matrix, having an eigenvector x with respect to lambda, if A is a matrix having an eigenvector x with respect to lambda, then k into x is also an eigenvector of A with respect to lambda. Then k into x is also an eigenvector of A with respect to lambda, where k is any non-zero constant. I repeat once again, if A is a matrix with x an eigenvector with respect to lambda, then k times x is also an eigenvector of matrix A with respect to lambda, where k is any non-zero constant. In the similar way, you can easily find the eigenvectors of A with respect to an eigenvalue 7. Now, this is by definition wise. Like this, you can easily find eigenvectors of any n cross n matrix just by taking definition. Now let us discuss one important shortcut to find the eigenvalues of a 2 by 2 real matrix. Eigenvectors of a 2 by 2 real matrix. Suppose I have a 2 by 2 matrix A, 2 by 2 real matrix, having eigenvalues lambda 1 comma lambda 2. Suppose I want eigenvectors of A with respect to lambda 1. If I want eigenvectors of this matrix with respect to lambda 1, calculate the matrix combination A minus lambda 2I. I am expecting eigenvector of this matrix with respect to lambda 1. So in that context, evaluate A minus lambda 2I. You will get a 2 by 2 matrix. So basically, in a 2 by 2 matrix, you will be having two columns. So this is column 1 and this is column 2. If either this or this is a non-zero column, if either C1 or C2, if either column 1 or column 2 is a non-zero column, then this non-zero column will be acting as eigenvector of this matrix with respect to an eigenvalue lambda 1. So the non-zero columns of A minus lambda 2I are nothing but eigenvectors of A with respect to lambda 1. Similarly, If I want eigenvectors of A with respect to lambda 2, take the reverse combination. Just you go for A minus lambda 1 I. You will get some 2 by 2 matrix. This is column 1, this is column 2. So either this or this is a non-zero column, then this will be acting as eigenvector of this matrix with respect to an eigenvalue lambda 2. Right? So therefore, suppose you may have one doubt. If it is a non-zero, assume that this is a non-zero column and this is a non-zero column, then which I need to select? Both you can take. Suppose if it is a non-zero column, this will be multiple of this. If it is a non-zero column, this will be non-zero multiple of this. Similarly, if both this column as well as this column are non-zero columns, then which I need to select? You can select both because both are eigenvectors. As I mentioned earlier, with respect to one particular eigenvalue, a matrix will have infinitely many eigenvectors. So you can choose anyone, everything is right. Therefore, if A is a 2 by 2 real matrix having eigenvalues lambda 1, lambda 2, then the non-zero columns of A minus lambda 2i are nothing but eigenvectors of A with respect to lambda 1. In the same way, the non-zero columns of A minus lambda 1i are nothing but eigenvectors of A with respect to lambda 2. Note this point. If A is a 2 by 2 real matrix, if A is a 2 by 2 real matrix having eigenvalues lambda 1 comma lambda 2, if A is a 2 by 2 real matrix having eigenvalues lambda 1 comma lambda 2, then point number 1, the non-zero columns of A minus lambda 2i, the non-zero columns of A minus lambda 2i are nothing but eigenvectors of A. The non-zero columns of A minus lambda 2i are nothing but eigenvectors of A with respect to lambda 1. Second point, the non-zero columns of A minus lambda 1i, the non-zero columns of A minus lambda 1i are nothing but eigenvectors of A with respect to lambda 2. Hope you understand these points. Suppose if you ask me, can I apply these shortcuts for 3 by 3? Yes, but it is a complicated procedure. Instead of doing that, better do that by using practice. That means A into x1 equal to lambda 1 into x1 by definition. So this is so flexible for 2 by 2. When I go for larger dimensions, do it by definition, right? So this is the end of the session. In the next session, we discuss examples of finding eigenvectors using these shortcuts and some more concepts on eigenvectors followed by classroom workbook. Thank you so much.